Hello students, welcome to Diksha Karnataka YouTube channel. In this video, I am going to discuss top 30 questions in dual nature of matter and radiations. Okay, so here these 30 questions are repeated in the KCET. Okay, so if you are able to solve these 30 questions, so definitely you will be able to counter these kind of questions in KCET. Okay, yeah, let us start. Question number 1. In an experiment to study photoelectric effect, the observed variation of stopping potential with frequency of incident radiation is as shown in the figure. The slope and y-intercept are respectively. So this is the given figure, right? Stopping potential versus frequency of the incident radiation graph, right? So this is the given graph, right? Isn't it? Okay. So first let us write the photoelectric equation. So what is the photoelectric equation? H into nu, that is energy of the incident photon, which is equal to here maximum kinetic energy of the photoelectron, that is E into Vs, right? Maximum kinetic energy of the photoelectron plus plus work function. Work function is H into nu naught. What is nu naught? Threshold frequency, right? Now I can write this equation as Vs equal to H into nu divided by E minus H into nu naught divided by E, right? So we know the straight line equation, right? Y equal to mx plus c. Now compare, right? So what is m? M is slope, right? So the slope m equal to h divided by E, right? And c, y-intercept, is equal to minus h divided by E into nu naught, right? So slope is h by E and y-intercept is minus h nu naught divided by E. So the correct option is D. Okay. Yeah. Next question. Question number 2. A 60 watt source emits monochromatic light of wavelength 662.5 nanometer. The number of photons emitted per second. Okay, we need to find number of photons emitted per second, right? We know that energy of the incident photon E equal to incident photons, okay, E equal to NHC divided by lambda, right? So what is power? Power P equal to energy divided by time, isn't it? Energy divided by time. Here time equal to 1 second. We need to find number of photons emitted per second, right? T equal to 1 second. So P equal to NHC divided by lambda, okay, per second, isn't it? Now here n per second is equal to P into lambda divided by h into c. Okay, P into lambda divided by h into c. Now n per second is equal to P. P is 60 watt into lambda is 662.5 nanometer, that is 10 to the power minus 9 meter, divided by h. H is Planck's constant, 6.62 into 10 to the power minus 34 into c. C is speed of light, 3 into 10 to the power minus 3 into 10 to the power minus 3 into 10 to the power 8 meter per second, not minus. Okay, 3 into 10 to the power 8 meter per second. So now n per second, that is number of photons emitted per second, n equal to here 10 to the power minus 9, right? This will be 100, right? Almost equal to 100, and then 3 20s are 60, right? So 10 to the power minus 34 into 10 to the power 8 is 10 to the power minus 26, right? Now 20 to the power minus 26 into 10 to the power minus 9, that is 10 to the power 15, right? 10 to the power minus 26 into 10 to the power minus 9, right? That is 10 to the power minus 17, okay? 10 to the power minus 17. So 20 into 100 is 2000, right? So it will be 2 into 10 to the power 17 into 10 to the power 3, that is 10 to the power 20. Okay, so the correct option is A. Next question, question number 3. In photoelectric experiment, if both the intensity and frequency of the incident light are doubled, both the intensity here, initial intensity of the incident light is I, okay, new intensity is I dash equal to 2I, and new frequency is 2F, okay, F is the initial frequency of the incident light, okay. Then the saturation photoelectric current, option A, is doubled. Okay, let's see. We know that the saturation current, the saturation photoelectric current, right? Saturation photoelectric current is directly proportional to the intensity of the incident light. Okay, intensity of the incident light. Saturation of the photoelectric current is directly proportional to intensity of the incident light, right? And saturation of the here saturation photocurrent does not depend on the frequency, does not depend on the frequency. If you double the intensity, the saturation photocurrent or photoelectric current will be doubled, right? And it does not depend on the frequency. So option A is the correct answer. Option B remains constant, wrong. Becomes 4 times, okay? So this is 4 times, wrong. Option D, have it wrong. So the correct option is A, okay? Question number 4. The kinetic energy of the photoelectrons increases by 0.52 electron volt when the wavelength of the incident light is changed from 500 nanometer to another wavelength which is approximately. Okay, so here the kinetic energy of the photoelectron increases by 0.52 electron volt, right? Okay, so K1 is the initial kinetic energy of the photoelectron, okay, maximum kinetic energy of the photoelectron or kinetic energy of the photoelectron. So from the Einstein's photoelectric equation, K1 equal to Hc by lambda 1, here lambda 1 equal to 500 nanometer, okay, minus phi. What is phi? Phi is work function, right? Now it is changed, right? Kinetic energy is changed. It is increased by 0.52 electron volt. Now new kinetic energy is equal to Hc by lambda 2 minus phi, right? So we need here, what is the change in kinetic energy? Change in kinetic energy is 0.52 electron volt, right? So take the difference between K2 and K1. So K2 minus K1 is equal to Hc by lambda 2 minus Hc by lambda 1. Anyway, phi and phi will get cancelled, okay? Now K2 minus K1 is 0.52 electron volt, okay, which is equal to here Hc is 1242 electron volt nanometer into 1 by lambda 2 minus 1 divided by 500 nanometer, right? So next 0.52 electron volt divided by 1242 electron volt nanometer, right, plus 1 divided by 500, right, which is equal to 1 divided by lambda 2, okay. So now solve this, okay, solve this, you will get lambda equal to 400 nanometer, so the correct option is D, okay. Yeah, next question, question number 5. The de Broglie wavelength of a particle of kinetic energy K is lambda. Okay, let us write the de Broglie wavelength in terms of kinetic energy, okay. So we know that kinetic energy Ke in terms of momentum is p square divided by 2m. So P equal to root of 2m into kinetic energy, right? Okay. The wavelength of the particle, if its kinetic energy is k by 4 is. Yeah. So what is the de Broglie wavelength? De Broglie wavelength lambda equal to h divided by p, right? So lambda is equal to h divided by root of 2m into kinetic energy, right? So from this I can conclude that lambda is inversely proportional to root of kinetic energy of the particle, right? So when the de Broglie wavelength is lambda, the kinetic energy of the particle is k, right? So here lambda dash divided by lambda is equal to here root of ke1 divided by root of ke2. Okay, lambda dash divided by lambda dash, okay, divided by lambda is equal to root of ke1 is root of k, right? Root of k divided by root of k divided by root of ke2 is root of k divided by 4, right? ke2 is k by 4, so root of ke2 is root of k by 4, right? So lambda dash equal to, solve this, you will get lambda dash equal to 2 lambda. So the correct option is D. Okay, yeah. Next question, question number 6. The work function of a metal is 1 electron volt. Phi is 1 electron volt. Light of incident wavelength 3000 angstrom, okay, 3000 angstrom is incident on this metal surface. The velocity of the emitted photoelectrons will be. Simple one and the direct question, right? First write the photoelectric equation. Here the photoelectric equation Hc by lambda, that is energy of the incident photon, is equal to maximum kinetic energy of the photoelectron, that is half m V max squared plus work function phi, right? We need to find V max, right? So half m V max squared, right? That is velocity of the emitted photoelectrons, right? Isn't it? So half m V naught squared is equal to here Hc divided by lambda minus phi, right? Now substitute the values. Okay, before that take half m to the other side. Okay, V max squared is equal to m divided by 2 by m, okay, 2 divided by m into Hc by lambda minus phi, right? So we need to find V max, right? So V max is equal to root of or 2 by m into Hc by lambda minus phi. What is m? M is mass of the electron, right? And we know Hc, right? H is Planck's constant, c is speed of light, lambda is 3000 angstrom, right? Phi is 1 electron volt, isn't it? So now solve this. Here V max is equal to root of 2 divided by m. M is 1.6, sorry, m is 9.1 into 10 to the power minus 31 kg. 9.1 into 10 to the power minus 31 into here Hc by lambda. Hc by lambda is 1242 electron volt nanometer divided by lambda is 3000 angstrom. I can write it as 300 nanometer minus 1 electron volt, right? Now solve this, you will get V max is equal to 10 to the power 6 meter per second, okay, which is approximately equal to 10 to the power 6 meter per second. So the correct option is D. Yeah. Next question, question number 7. A proton moving with momentum p1 has a kinetic energy 1/8 of its rest mass energy. So what is rest mass energy? Rest mass energy E equal to mc square, right? So the proton has kinetic energy 1/8 of its rest mass energy. So kinetic energy of the proton Kp is equal to mc square divided by 8. Another light photon having energy equal to the kinetic energy of the proton possesses momentum p2. Okay, so another light photon having energy equal to the kinetic energy of the proton, right? Kinetic energy of the proton possesses momentum P2. Then the ratio P1 minus P2 divided by P1, okay, so this is P1, is equal to, yeah, so let us find P1, right? So we know that P square by 2m is kinetic energy, right, or K. So P equal to root of 2mk or 2mke, okay, root of 2mk. So what is K? mc square by 8, right? So P1, that is momentum of the proton, P1 is equal to your root of 2m into mc square divided by 8, right? 2 4s are 8. So P1 is equal to mc by 2, right? mc by 2. Another light photon having energy equal to kinetic energy of the proton possesses momentum P2, right? So what is the kinetic energy of the proton? mc square divided by 8, right? So what is the energy of the incident photon? Energy of the incident photon is hc by lambda, right, which is equal to mc square divided by 8, right? So c will get cancelled, right? So what is h by lambda? H by lambda is momentum of the photon, right? Momentum of the photon is P2. So P2 is equal to mc by 8. Okay, we got the expression of P1 and P2, right? Now take the ratio P1 minus P2 by P1. So P1 minus P2 divided by P1 is equal to mc by 2 minus mc by 8 divided by mc by 2, right? Now the ratio P1 minus P2 divided by P1 is equal to, take mc by 2 as common, so this will be mc by 2 and mc by 2 will get cancelled, so this will be 1 minus 1 by 4, 1 minus 1 by 4 is 3 by 4. So the correct option is D. Okay, yeah. Next question, question number 8. According to Einstein's photoelectric equation, the graph between kinetic energy of photoelectrons ejected and frequency of the incident radiation. Okay, so we know that the graph between stopping potential, right, stopping potential and frequency of the incident light, right, frequency of the incident light, isn't it? So what is the graph? This is the graph, right, isn't it? This is the graph, right? So here what is stopping potential? Stopping potential is minimum negative voltage applied to the anode plate to stop the photocurrent, right? So that is equal to maximum kinetic energy of the photoelectron, right, isn't it? So this is the graph, maximum kinetic energy of the photoelectron and frequency of the incident radiation. So the correct option is D. Okay, yeah. Question number 9. The following graph represents the variation of photocurrent with anode potential for a metal surface. See, variation of photocurrent with anode potential, that is stopping potential, okay, stopping potential for a metal surface. I1, I2 and I3 represents intensities. Okay, I1, I2, I3 represents intensities, and gamma 1, gamma 2, gamma 3 represents frequency for the curve 1, 2, 3 respectively. Then option A says gamma 1 equal to gamma 2. No, here gamma 1 equal to gamma 2. Correct, right? Isn't it? See, here the stopping potential depends on the frequency. Okay, stopping potential depends on the frequency. It does not depend on the intensity. See here, gamma 1 equal to gamma 2, right? Isn't it? So stopping potential directly proportional to frequency. If frequency of the both lights are same, then the stopping potential will also be same, right? Gamma 1 equal to gamma 2, correct, right? I1 equal to I2, that is wrong, right? Isn't it? See, for curve 2, the photocurrent is more. For curve 1, photocurrent is lesser, right? Isn't it? So photocurrent depends on the intensity of the incident light, right? So here the photocurrent for second curve is more, right? For first curve it's lesser, isn't it? So I1 is not equal to I2. Okay, I1 is not equal to I2, and gamma 1 equal to gamma 2, or mu1 equal to mu2. Okay, so mu1 equal to mu2, I1 equal to I2, wrong. Here I1 equal to I3, given, wrong. I1 equal to I2, correct, right? Gamma 1 equal to gamma 2, correct. So option C is the correct answer. Okay. Next question, question number 10. Light of certain frequency and intensity incident on a photosensitive material causes photoelectric effect if both the frequency and intensity are doubled. The photoelectric saturation current becomes, see, again it's, the question is repeated, right? In CET also it is repeated. Okay, so here the photo current IP depends on, sorry, here the saturation current, okay, saturation current, that is photo current only. Okay, okay, photo current only, saturation current or photo current depends on intensity, okay, it does not depend on, it does not depend on frequency. Okay, so if the intensity of the incident light doubled, then the saturation photo current will also be doubled. Okay, so option D is the correct answer. Yeah. Next question, question number 11. The number of photons falling per second on a completely darkened plate to produce a force of 6.62 into 10 to the power minus 5 Newton is n. The wavelength of the light falling is 5 into 10 to the power minus 7 meter. Then we need to find the value of n. Okay, yeah. Planck's constant is given 6.62 into 10 to the power minus 34 joule second. Yeah. Here, what is the momentum? Okay, what is the de Broglie wavelength equation? Lambda equal to h divided by p, right? So p equal to h by lambda, right? P equal to h by lambda. Lambda value is given, right? Wavelength of the light, incident light is given, and h we know, right? Isn't it? So here p, the rate of change of momentum dp by dt is equal to h by lambda, right? Rate of change of momentum dp by dt is equal to h by lambda, right? So what is dt? dt equal to 1 second, right? dt is equal to 1 second, and here dp by dt will be force, right? Here number of photons falling per second, so that's why dt equal to 1 second, right? So the force F, dp by dt is force F is equal to h by lambda, right? So this is for one photon, right? And F is for force by the one photon, right? For n number of photons, F equal to n h divided by lambda, right? So this is the momentum of a photon, right? So there are n number of photons falling on a darkened plate, right? Isn't it? So F equal to nh by lambda, right? Now n equal to f lambda by h, f lambda by h. Now n equal to f is here 6.62 into 10 to the power minus 5, lambda is 5 into 10 to the power minus 7 whole divided by 6.62 into 10 to the power minus 34. Okay, so now 6.62 will get cancelled. This will be 10 to the power minus 29, right? 10 to the power minus 5 by 10 to the power minus 34 is 10 to the power 29, not minus 29. 10 to the power 29 into 10 to the power minus 7 is 10 to the power 22. So n equal to 5 into 10 to the power 22. So the correct option is B. Okay, yeah. Next question, question number 12. Maximum kinetic energy of the emitted photoelectrons depends on. Okay, so maximum kinetic energy of the photoelectrons depends on frequency of the incident light. Okay, frequency of the incident light. So option B is the correct answer. Frequency of the incident radiation. Okay, not speed of the incident radiation, not intensity, okay, not number of photons in the incident radiation. No, incident radiation, okay, not rotation. Radiation. Yeah. So option B is the correct answer. Next question, question number 13. A proton and an alpha particle, okay, this is alpha particle. Proton and an alpha particle are accelerated through the same potential difference V. The ratio of their de Broglie wavelengths is, okay, so de Broglie wavelength lambda equal to h divided by p, right? So proton accelerated through a proton and alpha particle accelerated through the same potential difference. When proton or alpha particle accelerated through a potential difference, what happens? It gains kinetic energy, right? So electrostatic potential energy QV equal to kinetic energy of the proton or alpha particle, right? So we know that p square divided by 2m, which is equal to kinetic energy k, right? Now p equal to root of 2mk, right? P equal to root of 2mk. So k is qv, right? So p equal to root of 2m q into v. Okay. So here mass of the alpha particle is 4 times mass of the proton, and charge of the alpha particle is equal to 2 times charge of the proton. Okay. So now what we need to find here, we need to find the ratio of their de Broglie wavelengths, right? That is ratio here the ratio of the de Broglie wavelength of the proton to the alpha particle, which is equal to root of 2 m alpha q alpha into v, right, divided by root of 2 mp qp into v. V will get cancelled, 2 will get cancelled. What is m alpha? M alpha is 4 mp, q alpha is 2 qp, right? So lambda p divided by lambda alpha is equal to here root of 4 mp into 2 qp divided by mp into qp. mp into qp, mp into qp will get cancelled. 4 into 2 is 8. So lambda p divided by lambda alpha is equal to root of 8 is 2 root 2. So the correct option is B. Okay. Yeah. Next question. Question number 13. An electron is moving with an initial velocity v vector equal to v naught I cap, and in a uniform magnetic field b vector equal to b naught j cap, then its de Broglie wavelength, okay, decreases with time, remains constant, increase and decrease periodically, increases with time. Okay, let's see. Here when electrons enters into a uniform magnetic field perpendicularly, what happens? Electron takes circular path, right? Electron takes circular path, and it is a uniform circular path, right, or uniform circular motion. Uniform circular motion, right? Electron takes uniform circular motion, isn't it? Right? So in uniform circular motion, speed of the particle remains same or constant, right? Isn't it? So it remains same. So the de Broglie wavelength here, lambda equal to h divided by mv, right? Momentum is mv. So if speed is constant, then de Broglie wavelength remains constant, right? Isn't it? Here v is constant or momentum is constant. Lambda will also be constant, right? So the correct option is B. Okay. Yeah. Next question. Question number 15. A particle is dropped from a height h. The de Broglie wavelength of the particle depends on height s. Okay, so when particle dropped from a height h, right? So what is the velocity gained by the particle, right? So from the third equation of motion, v square equal to u square plus 2gh. Okay, here u is 0, v equal to root of 2gh. So this is the velocity gained by the particle, right? Now de Broglie wavelength lambda equal to h divided by m into v. Momentum is m into v. V is root of 2gh. 2gh. Here h is constant. That is Planck's constant is constant only, right? M is also constant. G is also constant. So lambda is inversely proportional to h to the power 1 by 2. Okay. So or lambda directly proportional to h to the power minus 1 by 2. Okay. So the height, de Broglie wavelength of the particle depends on height as h to the power minus 1 by 2. So option B is the correct answer. Okay. Yeah. Question number 16. From the following graph of photocurrent against collector plate potential for two different intensities of light I1 and I2, one can conclude. Okay, so here this is the photocurrent and collector plate potential, right? There are two curves. Intensities of these two lights is I2 and I1, right? Option A says I1 equal to I2. Absolutely wrong, right? Why? Here the photocurrent for first incident radiation is lesser compared to the second one, right? So we know that photocurrent depends on intensity of the incident light, isn't it? Photocurrent depends on intensity of the incident light, isn't it? So for first curve, here the photocurrent is lesser compared to the second, right? So intensity of the first light is lesser than intensity of the second light. So the correct option is C. Okay. Yeah. Question number 17. The variation of photocurrent with collector potential for different frequencies of incident radiation nu1, nu2 and nu3 as shown in the graph. Then, okay, so these three are the curve, right? Nu1, nu2, nu3, right? And for these three incident radiation, photocurrents are V01, V02, V03, right? So we know that stopping potential V depends on frequency of the incident light or frequency of the incident radiation, right? Isn't it? So for first light, the stopping potential is lesser compared to the second one and the third one, right? For second one, it is lesser compared to the third one, right? So therefore, here nu1 is lesser than nu2 is lesser than nu3. Okay. So the third incident light is has the highest frequency. Okay. So the correct option is C. Understood? Yeah. Next question. Question number 18. The de Broglie wavelength of an electron accelerated to a potential of 400 volt is approximately. Okay. So here the direct question, right? De Broglie wavelength lambda equal to h divided by p, right? P is momentum, h is Planck's constant, lambda is de Broglie wavelength. Now we know that kinetic energy of the particle is equal to square of the momentum divided by 2m. M is mass of the particle, right? Now P is equal to root of 2m into k, right? So here electron accelerated through a potential difference 400 volt. That is, electron gains kinetic energy, right? Electron gains kinetic energy and electric potential of the electron or potential energy of the electron decreases, right? So gain in kinetic energy is equal to loss in potential energy. The electrical potential energy is QV, which is equal to kinetic energy K, right? So now I can write momentum P equal to root of 2m Q into V, right? Now here lambda is equal to h divided by root of 2m into Q into V. What is Q? Charge of the electron, right? So it is E. Okay, I can write it as E. Okay. Now lambda is equal to here h divided by root of 2me is equal to 12 12.27. Okay, 12.27 angstrom. Okay, 12.27 angstrom. Okay, so now lambda is equal to 12.27 angstrom divided by root of V, that is 400, right? Now lambda is equal to 12.27 divided by root 400 is 20 angstrom. Okay, lambda is equal to, now solve this. Okay, solve this, you will get 0.06 nanometer. Okay, 0.06 nanometer. Understood? Yeah. Next question, question number 19. Find the de Broglie wavelength of an electron with kinetic energy of 120 electron volt. Same type question, right? Here de Broglie wavelength lambda equal to h divided by p. Lambda equal to h divided by p is root of 2mk, right? So lambda is equal to h is here 6.62 into 10 to the power minus 34, right, divided by root of electron, right? So 2 into mass of the electron, right? Mass of the electron is here 9.1 into 10 to the power minus 31 kg into k. K is kinetic energy of the electron, right? So that is 120 electron volt. So you have to convert it into joule. So 1.6 into 10 to the power minus 19. Okay. So now solve this. Okay. You will get the value of lambda as 95 picometer. Solve this, you will get lambda as 95 picometer. Okay. So the correct option is C. Understood? Yeah. Next question, question number 20. Light of two different frequencies whose photons have energies 1 electron volt and 2.5 electron volt respectively successively illuminates a metallic surface whose work function is 0.5 electron volt. The ratio of the maximum speed of the emitted electrons will be. Okay, let us write the photoelectric equation. The photoelectric equation is energy of the incident photon, that is hc by lambda, is equal to maximum kinetic energy of the photoelectron, right? So maximum kinetic energy of the photoelectron is half mv max squared, half mv max squared plus stopping potential phi, right? Stopping potential phi. Now what is the energy of the frequency here? What is the energy of the incident photons? 1 electron volt and 2.5 electron volt, right? So here this will be energy of the incident photon 1 electron volt, okay, which is equal to half m v max squared plus 0.5 electron volt, that is work function, right? So this is v max square 1, okay, v max square 1. So half m v max square 1 is equal to 0.5 electron volt, right? Similarly for second light or second photon, here half m v max square 2 is equal to 2.5 minus 0.5, right? So half m v max square 2 is equal to 2 electron volt, right? So now divide the second equation by first equation, okay, then you will get v max square 2, right? V max square 2 divided by V max square 1 is equal to, so this will be 0.5 divided by 2, right? Now V max 1 by V max 2 divided by V max 1 right, which is equal to, sorry, this will be 2 by, here this will be 2 by 0.5, okay, 2 by 0.5, 2 divided by 0.5, okay. So now Vmax 1 by Vmax 2, Vmax 1 by Vmax 2 equal to, here 1 by 4, right, 2 by 0.5 is 4, so Vmax 1 by Vmax 2 is 1 by 4, right. So the ratio will be 1:4. So the correct option is A. Okay. Yeah. Next question. Question number 21. What is the de Broglie wavelength of the electron accelerated through a potential difference of 100 volt? We solved the same type of question, right? See, these kind of questions are repeated, continuously repeated, right? So the de Broglie wavelength, lambda equal to 12.27 angstrom divided by root of potential difference V, right? So what is root V? 100 volt. So lambda is equal to 12.27 divided by root of 100 angstrom. Root of 100 is 10. So lambda equal to 1.227 angstrom. So the correct option is D. Okay. Yeah. Next question. Question number 22. The maximum kinetic energy of the photoelectrons depends only on. Okay, maximum kinetic energy of the photon depends only on the frequency of the incident light. Okay, frequency of the incident light. So the correct option is D. Okay, yeah. Next question. Question number 23. Silver has a work function of 4.7 electron volt, phi equal to 4.7 electron volt. When the ultraviolet light of wavelength 100 nanometer, okay, so this is nanometer, is incident upon it, a potential of 7.7 volt is required to stop the photoelectrons from the reaching the collector plate. How much potential will be required to stop the photoelectrons when the light of wavelength 200 nanometer, again is nanometer, is incident upon silver? Okay, first write the photoelectric equation. Energy of the incident light is equal to maximum kinetic energy of the photoelectron plus work function phi, right? So here maximum kinetic energy of the photoelectron is E into Vs, right? It is E into Vs. Vs is stopping potential, right? So we need to find stopping potential for 200 nanometer incident wavelength, right? Now here Hc is 1242 electron volt nanometer divided by 200 nanometer equal to E into Vs plus phi. Here phi is 4.7 electron volt. 4.7 electron volt. Okay. So anyway, both side electron here E term will get cancelled. Only potential, right? That will remain, right? So now Vs, the stopping potential, equal to solve this, you will get 1.5 volt, right? See here, all these things, that is the 100 nanometer wavelength, right? First wavelength, and then the stopping potential, all these things are useless, right? Useless data, right? Isn't it? So they deliberately made the big question, right? Isn't it? The lengthy question, right? Isn't it? To waste the time, yeah. To waste our time, yeah. Next question. Out of a photon and an electron, the equation E equal to Pc is valid for. Okay, so we know that when particle moves with the relativistic speed means the speed of the particle is almost equal to the speed of the light, almost equal to, not exactly equal to. So then energy of that particle E equal to root of P square C square plus M square C to the power 4. Okay. So for photon, okay, here P is the momentum, C is speed of light, M is rest mass. Okay. So for momentum, rest mass is 0. Sorry, for photon, rest mass is 0, right? For photon, rest mass is 0. So E equal to root of P square C square. E equal to P into C. So this is for photon. Okay. Instead of photon, if they give electron, then m equal to 9.1 into 10 to the power minus 31 kg, right? That is the rest mass of the electron. So it is not zero. Then energy is different, right? So E equal to Pc for photon. Photon only. So option C is the correct answer. Okay. Next question. Question number 25. When a centimeter thick surface is illuminated with the light of wavelength lambda, the stopping potential is V. Okay, I will directly write the photoelectric equation here. Hc by lambda. Lambda is the incident wavelength. Okay. Hc by lambda equal to here maximum kinetic energy of the photoelectron, right? Maximum kinetic energy of the photoelectron is E into V. V is stopping potential, right? Plus work function phi. Yeah. When the same surface is illuminated by a light of wavelength 2 lambda. So this is the first equation. Second equation, Hc by 2 lambda. The stopping potential is V by 3. That is E into V by 3 plus phi. So this is the second equation. Threshold wavelength for metallic surfaces. So we need to find threshold wavelength, right? Isn't it? So the work function phi equal to Hc by lambda naught, right? Work function phi equal to Hc by lambda naught. Okay, so I can write the first equation as phi equal to Hc by lambda. Phi equal to Hc by lambda minus E into V, right? Now substitute this equation to the second equation. Now Hc by 2 lambda minus equal to E into V by 3 plus Hc by lambda minus EV, right? Here Hc by lambda minus EV is the first equation. Okay, this is the first equation, and substitute the second equation phi to the second equation. Hc by 2 lambda equal to EV plus Hc by lambda minus EV. Yeah. Now here solve this. You will get Hc by 2 lambda equal to 2 into EV by 3, right? 2 into EV by 3. So Hc by 2 lambda equal to 2 into EV by 3, right? Substitute this equation Hc by 2 lambda to the second equation, right? You will get here 2 EV by 3 minus EV by 3 is equal to phi. Phi is Hc by lambda naught, right? So 2 EV by 3, EV by 3 is minus EV by 3, sorry, plus EV by 3, right? So Hc by lambda naught is equal to EV by 3, right? Substitute here, right? Phi is Hc by lambda naught. Substitute Hc by lambda naught to the first equation or second equation. Okay, so then you will get lambda. Okay, substitute Hc by lambda naught. Okay, which is equal to EV by 3 equal to the second equation. Okay, then you will get lambda naught is equal to 4 lambda. Okay, lambda naught is equal to 4 lambda. So this is Hc by lambda naught. Phi is Hc by lambda naught, 2 Hc by lambda naught. Hc by 2 lambda equal to 2 Hc by lambda naught. So lambda naught equal to 4 lambda, right? So the correct option is B. Yeah, next question. Question number 26. A light of wavelength lambda strikes a photoelectric surface and electrons are ejected with kinetic energy K. If K is to be increased to exactly twice its original value, the wavelength must be changed to lambda dash such that. Okay, so there are two situations. First, the light of wavelength lambda strikes on a photoelectric surface, right? The second case, here we need to find, okay, lambda dash is the second wavelength. It falls on the same photosensitive material, right? So we need to find the lambda dash, right? The kinetic energy is to be increased exactly twice its original value, right? Okay, so what is the photoelectric equation? Here the photoelectric equation, Hc by lambda, that is energy of the incident light, Hc by lambda equal to maximum kinetic energy plus phi, right? So I can rewrite this equation as K equal to Hc by lambda minus phi. right? So this is the first equation. Now kinetic energy is to be increased exactly twice its original value. So that is 2k is equal to hc by lambda dash minus phi, right? Minus phi, isn't it? So this is the second equation, right? Second equation. So now here, or we can rewrite this equation as, okay, I will rewrite this equation as hc by lambda dash equal to 2k plus phi, okay, 2k plus phi. So now divide the first equation, or here this is the equation star. Divide the equation star to this equation, equation 3, okay. So here lambda dash divided by lambda is equal to, so this will be k plus phi divided by 2k plus phi, 2k plus phi. Now take k as common, lambda dash divided by lambda is equal to here 1 plus phi divided by k whole divided by 2 plus phi by k, okay, 2 plus phi by k. So definitely here the whole value this is greater than 1, right? So it is definitely greater than 1, right? Isn't it? Or greater than half. So it is definitely, so it will be definitely greater than half, right? Isn't it? So phi by k cannot be equal to 0, right? Phi by k cannot be equal to 0. It is greater than 0. So this whole equation is greater than half, right? Isn't it? So lambda dash by lambda is greater than half, right? Lambda dash by lambda greater than half. So lambda dash is greater than lambda by 2, right? Okay, now we need to find whether lambda dash is lesser than lambda or not, right? Okay, if you increase the value of k, what happens here? If you increase the value of k, here the both side increases equally, right? If you increase the value of k, both side increases equally, right? So it will increases equally, right? So the value will remain same, isn't it? So lambda dash is always lesser than lambda, right? Lambda dash is always lesser than lambda, isn't it? So this is the condition, okay. So the correct option is C. Yeah. Question number 27. The ratio of the momenta of an electron and an alpha particle which are accelerated from rest by a potential difference of 100 volt. Okay. So here ratio of the momenta of an electron and an alpha particle, right? Isn't it? So momentum P equal to root of 2 mk. P equal to root of 2 mk. When particle, charged particle accelerated through a potential difference, what happens? It gains kinetic energy, right? So the kinetic energy, gain in kinetic energy is equal to loss in electrical potential energy, right? So momentum P equal to root of 2m q into v, right? So for electron, momentum will be root of 2 me into 2 me into qe is here, q is e, okay, into 100%, into 100 volt, right? So for alpha particle, okay, for alpha particle which is equal to root of 2 m alpha into what is the charge of the alpha particle? It is 2 times charge of the proton, right? Charge of the proton and charge of the electrons are equal, right? So 2 times charge of the proton, so 2e into 100%, right? Now the ratio of the moment of the electron to the alpha particle, right, which is equal to root of 2m e into 100 divided by root of 4 me into e into 100. me into e into 100, me into e into 100 will get cancelled. So pe by p alpha, sorry, this will be alpha, m alpha, okay, m alpha okay, not me. So E into 100 will get cancelled, okay. So this will be root of me by 2 m alpha, root of me by 2 m alpha. So the correct option is D, okay. This is not me, this is m alpha, okay. So E into 100 will get cancelled. So me by 2 m alpha, root of 2 me by 2 m alpha, okay. Next question, question number 28. The kinetic energy of an electron is E when the incident wavelength is lambda. To increase the kinetic energy of the electron to 2E, the incident wavelength must be. Okay, we need to find new incident wavelength. The same question, right? We solved, right? Okay. So here, when the incident wavelength is lambda, right? The kinetic energy of the photoelectron is E, right? So Hc by lambda equal to E plus phi, right? So new energy of the incident wavelength lambda dash is equal to new energy of the incident light of wavelength lambda dash, okay. So that is Hc by lambda dash is equal to here 2E plus phi. So this is the first equation and here this is the second equation, okay. Now divide the first equation by second equation. You will get lambda dash, okay, lambda dash Hc by or okay, we need to write in terms of Hc, right, okay. So I can write the first equation as phi equal to Hc by lambda, phi equal to Hc by lambda minus E. Now substitute expression of phi to second equation. Now Hc by lambda dash equal to Hc by lambda dash is equal to 2E plus Hc by lambda minus E, right. Now here we need to find lambda dash, 2E minus E is E, right. So Hc divided by lambda dash is equal to Hc by lambda, right, plus E, right, Hc by lambda plus E. Now 1 divided by lambda dash is equal to 1 divided by lambda plus E divided by Hc, right. Now 1 divided by lambda dash is equal to Hc plus E lambda divided by lambda into Hc. So lambda dash is equal to lambda Hc divided by Hc plus E lambda. So the correct option is C, okay. Question number 29. An electron of mass m and a photon have same energy E. The ratio of de Broglie wavelength associated with them. Okay. So we know that energy of the photon E equal to momentum of the photon into c. C is the speed of the light in vacuum, right? Okay. An electron of mass m and a photon have same energy E, right? Okay. The ratio of the de Broglie wavelength associated with them, right? We need to find the ratio of the de Broglie wavelength of the electron to the photon, right? Okay. So what is the momentum of the electron? Momentum of the electron Pe equal to m into v, right? Pe equal to m into v, right? Okay. So both have same energy, right? So here energy of the electron E equal to P square divided by 2m, right? So P equal to root of 2m into E. So this is momentum of the electron, right? Momentum of the electron. So now what is the de Broglie wavelength of the photon? Lambda equal to h divided by p, right? Lambda equal to h by p, isn't it? So I can write this p as E divided by c, right? So now de Broglie wavelength of photon is equal to h divided by E divided by c. So lambda p equal to CH divided by E, right? So what is the de Broglie wavelength of the electron, right? So de Broglie wavelength of the electron is H divided by P, a momentum of the electron, right? Momentum of the electron is root of 2m into E, right? So now de Broglie wavelength of the ratio of de Broglie wavelength of electron to the photon is equal to H divided by root of 2me whole divided by CH divided by E, right? So now solve this. Here lambda E by lambda P is equal to H. H will get cancelled. So now 1 by C into root of, here E will go to the numerator, right? So if you take E under root, so you will get here this will be E square, right? So E square divided by 2me. So now the ratio lambda E by lambda P. Lambda E by lambda P is equal to 1 divided by C into root of E divided by 2m. So the correct option is A. Okay. Yeah. Next question. Question number 30. An electron of mass m accelerated from rest through a potential difference V volt in vacuum, its final speed will be. Okay, so here electron accelerated through a potential difference V from rest, right? Here the potential difference is V. Okay, here the velocity of the electron is 0. Initial velocity of the electron is 0. Final velocity is V. Okay, electron accelerated through a potential difference V, right? So when electron accelerated through a potential difference V, what happens? Here it gains kinetic energy or it gains velocity, right? So we need to find final speed of the electron, right? So when it gains kinetic energy, it loses its potential energy also, right? Electric potential energy. So that will be here E into V, electric potential energy, which is equal to gain in kinetic energy, right? So final speed V equal to root of, final speed V equal to root of 2eV divided by m. That's it. So the correct option is B. Okay. Yeah. Okay. Thank you. Thank you so much for watching this video. Okay. So if you love this video, please like and share. Okay. If you want to watch more such videos, please subscribe. Thank you.